Hello students, in the present video lecture, we'll discuss about basic processing units. A computer system has one functional unit which executes machine instructions. This unit communicates with and coordinates the activities of other subsystems within the computer. This unit is called as Central Processing Unit or CPU, which is also referred as Instruction Set Processor or ISP, or else simply we can refer this as a processor. So in the present session, we'll describe the internal structure of the processor and we'll explain how it performs the operations of fetching, decoding and executing instructions of the program. A typical computing task consisting of series of steps of instructions that makes a single program. An instruction is executed by carrying out a sequence of elementary operations. So the performance of the computer is determined by the instruction count, clock cycle time as well as clock cycles per instructions. The implementation of processor determines both the clock cycle time and CPI. So now we'll consider some fundamental concepts. In order to execute an instruction, processor has to perform 3 steps. Initially, the processor need to fetch the contents of memory location pointed by PC. Initially, the processor will fetch the content of memory location which was pointed by program counter or PC. Content of these location is an instruction to be executed. The instructions are loaded into instruction register. Symbolically, the operation can be written as initially during fetch phase, content of program counter, it will be loaded into instruction register. And after that, the content of PC will be incremented by 4. So that means the new value of PC becomes PC is equal to PC plus 4 in order to fetch the next instruction. So these two steps are involved or referred as fetch phase. These two steps are called as fetch phase. So this next phase is execution phase. During execution phase, the instructions can be executed either the type of operation specified may be either arithmetic operation or else logical operation. The respective operation can be considered with respect to the type of instruction given, type of operand given in the instruction. The operation specified by an instruction can be carried out by performing one or more of the following actions. Initially, read the contents of a given memory location and load them into a register. Initially, the content of read the content of a given memory location. After that, load the content into a processor register. So either the type of operation may be read the data from one or more registers. So depending upon that, perform an arithmetic or logical operations, and finally place the data as well as, that means results, into a register. After performing the execution of the instruction, The final result can be stored either in a register or else in the given memory locations. So these are the operations which can be specified by an instruction, and we can consider the type of operation may be either arithmetic operation or logical operation. So the diagram shows main hardware components of a processor. Processor basically consisting of a register file, arithmetic and logical unit, control circuitry and special registers like instruction register and PC, and followed by processor memory interface unit. Single bus organization. Arithmetic and logic unit and all the registers are interconnected via a single common bus. In order to know how operations can be implemented, we need to know the internal structure of the processor. The various functional blocks of the CPU can be organized and interconnected in a variety of ways. The simple organization in which the arithmetic and logic unit and all the registers are connected using a single bus. So we can consider ALU, we can consider arithmetic and logic unit, all the registers are connected to a single common bus, This bus is internal to the processor. The data and address lines of the external memory bus are connected to the internal processor via memory data register, that is MDR and MAR. So the data as well as address lines of the external memory bus are connected to the internal processor bus by considering two registers like MDR as well as MAR. MDR is used in order to carry the data and MAR is used in order to carry the address. MDR has two input and two outputs. MAR has two inputs and two outputs. Data may be loaded into MDR either from the memory bus or from the processor bus. So we can consider the data can be loaded either from the processor bus, or else the data can be loaded from the memory bus into the special register called as MDR. MAR's input is connected to the internal bus and output is connected to the external bus. So MAR input is connected to the internal bus or single bus, and output is connected to the external bus. Instruction decoder and control unit is responsible for issuing control signals. What is the use of control unit? So which will issue the control signals to all the units inside the processor. Implementing the actions specified by the instruction, so that will be loaded in the instruction register. So we are also having some general purpose registers like R02, R0, R1 and so on, Rn-1, which is also located within the processor. The programmer can access these registers for general purpose use. The general purpose registers can be accessed by the programmer in order to perform any general purpose task. Only processor can access three registers. that is Y, Z and temp. So processor can access three registers Y, Z and temp for temporary storage during program execution. The programmer cannot access these three registers. Only processor can access the temporary registers. In ALU, it consisting of two inputs. So we can consider two inputs. One is A and other one is B. Input A gets the operand from the output of the multiplexer. So input A gets the input from output of MUX, output of the multiplexer. Similarly, input B gets the operand directly from the processor bus. So this input B, it will be directly from the processor bus. There are two options provided for A input of the ALU. MUX is used to select one of the two inputs. MUX selects either output of Y or constant value 4, which is used in order to increment the content of PC. So the diagram shows single bus structure. So the bus is internal to the processor. The data and address lines of the external memory are connected to the internal processor bus via memory data register and memory address register. So the data may be loaded into MDR either from the memory bus or from the internal processor. So the data may be loaded from the processor bus or else from the external bus. Similarly, the input of MAR is connected to the internal bus. Input is from the internal bus itself and output is connected to output of MAR is connected to the external bus. So this is external bus. Output is connected to the external bus. The input of MAR is connected to internal bus and output is connected to the external bus. The control lines of the memory bus are connected to the instruction decoder. So here we can observe that we are having some control signals or control lines are connected to the instruction decoder and control logic. So this unit is responsible in order to issue the signals that control the operations of all the units. So this will issue some set of signals and those signals are called as control signals. The functional elements like PC, MAR, MDR, R0, R1, etc. are connected to the internal bus. So we can observe that we are having PC, MAR, MDR as well as R0 to Rn-1. So everything is connected to the system bus. The bus connection is also considered with respect to the single system bus along with special registers. So the number of functions of processor register, so that is R0 to Rn-1, can be used in order to perform any general purpose task. So other registers we are using it as Y as well as one more is Z and temp. Those temporary registers can be exclusively used by the processor in order to perform the operations. So we can say that such temporary registers can be used by the processor during the execution of some instruction, and we can observe that we are having one MUX block. which selects either the value y or else a constant 4 as input. So this is provided as input A to the ALU, and input B is directly considered from the system bus, obtained directly from the processor bus. Thus, the select line of mux can be either select 4 or select 4. This select line may be either select 4 or else select Y. Select 4 or select Y. The registers, the ALU and the interconnecting bus are collectively referred as data path of the processor. The instructions are usually categorized into 3 classes: memory reference, arithmetic and logic operations, and branch instructions. The actions required to complete the instruction depends upon the instruction class. An instruction is executed by performing one or more of the following operations: the transfer of word of data from one processor register to ALU, transfer a word of data from one register to another or to the ALU, perform arithmetic and logic operation and store the result in the register, fetch the contents of a given memory location and load them into a register. Finally, store the data from the register into a given memory location. The major disadvantage of single bus structure is only one data word can be transferred over the bus in a clock cycle. In a given clock cycle, we can transfer a single or only one data word. The major solution is to provide multiple internal paths. Multiple paths allows several data transfer to take place in parallel. So parallelly we can transfer several data or several blocks of data in parallel. So next we will consider register transfer. Instruction execution involves a sequence of steps in which the data are transferred from one register to another. For each register, there will be two control signals like RIN and ROUT. So these are called as gating signals. For example, if I consider one register RI and each register will be considering two gating signals. So RI in and RI out. So these special signals are called as gating signals. If RI in is 1, then the data on the bus is loaded into RI. So whenever the value of gating signal, if it is 1, the data can be loaded into the register RI. And when RI out is equal to 0, bus can be used for transferring the data from the other register. So whenever RI out is equal to 0, that means the bus can be used in order to transfer the data from the other register. For example, move R1, R2. This transfers the content of register R1 to register R2. This can be accomplished as enable the output of the register 1 by setting R1 out to 1. So this places the content of R1 on the processor register. So later enable the input of register R2 by setting R2 out to 1. So this loads the data from the processor bus into the register R4. So in this case we can consider the register as R2. Input and output gating signals for registers. Instruction execution involves sequence of steps in which the data are transferred from one register to another. For each register, there will be two control signals can be used to place the contents of that register on the bus or load the data from the bus into the register. So here we can observe that here the RI consisting of two gating signals. So that is RI in and RI out. Similarly, Y in and Y in followed by here Z in and Z out. Each and every registers consisting of the gating signals. So when RIN is set to 1, the data on the bus are loaded into RI. When RI out is set to 1, the contents of RI are placed on the bus. So whenever RI in, if it is set to 1, the data from the bus can be loaded into RI. From the bus, the data from the bus can be loaded into RI. So now the data is copied whenever this gating signal. So since this signal is closed now, whenever RIN is 1, the data from the bus can be loaded into the register RI. And whenever RI out is equal to 0, whenever RI out equal to 0, the data cannot be transferred between the processor, bus as well as register. But whenever RI out is equal to 1, the content of RI are placed on the bus. Once again, whenever this switch is closed, the content of RI can be copied into the bus. So whenever RIN is equal to 1, the data can be copied from the bus into the register. Whenever RI out is equal to 1, the data can be copied from the register into the bus. All operations and data transfer within the processor takes place within time period defined by the processor clocks. The control signals that governs particular transfer are asserted at the start of clock cycles. The register consists of edge-triggered flip-flops, and clocking methodology defines the timing of read and write operations. If the signals written at the same time is read, the final value is ambiguous. Hence, edge-triggered clocking methodology is used in all the processors. When edge-triggered flip-flops are not used, two or more clock signals may be required for proper transfer of data. So that is known as multi-phase clocking concept. So the register transfer, registers need input as well as output gating signals. When RIN control signal for input of RI, when RIN is equal to 1, data available on the register RI. When RI out control signal for output of RI, when RI out is equal to 1, the content of RI are placed on the bus. For example, the transfer of contents R1 to R4. Enable output of R1 by setting R1 out is equal to 1. Enable input of R1 by setting R4 in is equal to 1. Register transfers. A 2-input multiplexer is used to select the data applied to the input of an edge-triggered D flip-flops. When the control input RI in is equal to 1, the multiplexer selects the data from the bus. Whenever RIN in is equal to 1, the multiplexer will select the data on the bus. This data will be loaded into the flip-flop. So now we can load the data into the flip-flop. At the rising edge of the clock, when Ri in is equal to 0, the multiplexer feeds back the value currently stored in the flip-flop. The Q output of the flip-flop is connected to the bus via tri-state gate. When Ri out is equal to 0, the gate's output is in the high impedance level. This corresponds to the open circuit state of the switch. When Ri out is equal to 1, the gate drives to the bus to 0 or 1 depending upon the value of Q. Input and output gating for one register bit. A 2-input multiplexer is used to select the data applied to the input of an edge-triggered flip-flop. Whenever RIN is equal to 1, a mux selects the data on the bus. This data will be loaded into flip-flops at rising edge of the clock. RIN is equal to 0, mux feed back the value currently stored in the flip-flop. Q output of flip-flop is connected to bus via tri-state gate. Whenever R out is equal to 0, gate's output is in the high impedance state. Whenever the value is equal to 1, the gate drives the bus 0 or 1 depending upon the value of Q. Performing an arithmetic or logic operations. So we'll consider one example. R3 is equal to R1 plus R2. That means content of R1 plus R2 will be stored in the processor register R3. So we can consider the sequence of operations that can be carried out. That is, the first step, that is R1 out, comma Y in. That means the content from register R1 are loaded into temporary register Y. The content of R1 during step 1, the content of R1 with the gating signal, that is R1 out, will be set to 1. So that will be copied into the temporary register Y. So now R2 out, the output of R2 out, select Y, add, Z in. The contents from Y and from the processor register R2 are applied to A as well as B inputs of the ALU, and later the addition can be performed and the result can be stored in the register Z in. So now we can consider the contents of Y, contents from Y and from the register R2, that contents will be given as input to the ALU, that is A as well as B, and those values will be added, that is addition operation is performed, and finally store the result in the temporary register Z in. So now we are having in Z in, we are having the value R1 plus R2. So finally we have to store R1 plus R2 into the register, general purpose register R3. So that means Z out, R3 in. So the result is stored in the register Z, and that value or information can be loaded into the processor register R3. So this is how we can consider the series of operations in order to perform R1 plus R2 is equal to R3 by considering the gating signals or gating signals like R1 out, R2 out, Z out, R3 in, Z in, etc. Initially, during step 1, the contents from register R1 are loaded into the register Y. During step 2, contents from Y and from the register R2 are applied as inputs A as well as B to the ALU, and later addition can be performed and results will be stored in the temporary register Z in. And finally, the final result, that is R2 plus R1, will be stored in the register R3 in by copying Z out, R3 in.